In this video, I want to look at vector-valued functions as they relate to position, velocity, speed, and acceleration. If we're given well-defined forces acting on an object and some initial condition, it's possible to determine the motion of the object for all future times. The study of motion begins with a look at motion in one direction, and we've already seen that when I talk about things traveling a straight line. And as we became comfortable with that, we began to extend the ideas of motion into two dimensions where things would travel in an XY plane. And now we finally have the tools we need to be able to go beyond two dimensions and work with motion in three dimensions, or motion in space. There are four basic quantities that we'll be working with when we talk about an object in motion in three-dimensional space. There'll be the position, the velocity, the speed, and the acceleration. The vector-valued function for position is typically expressed as the vector r of little t, given by the components x of t, y of t, and z of t. The vector-valued function for velocity is typically expressed as the vector v of little t, which is the first derivative of the vector r of little t, and that is given by the components x prime of t, y prime of t, and z prime of t. The magnitude of the velocity vector function is the scalar quantity that gives me the speed of the object. This is typically written as the magnitude of the vector v is given by the square root of x prime of t squared plus y prime of t squared plus z prime of t squared. The vector-valued function for acceleration can be expressed as the vector a of little t is equal to the first derivative of the velocity vector, or the second derivative of the position vector, and it has the components x double prime of t, y double prime of t, and z double prime of t. So let's work an example. I want to find the velocity, speed, and acceleration of an object whose position is given by the vector with components 2e to the 2t plus 1, e to the 2t minus 1, and 2e to the 2t minus 10, where t is greater than or equal to 0. I have the position function. The velocity vector is the first derivative of the position vector. This means I will take the derivative with respect to t of each of my components, 2e to the 2t plus 1, e to the 2t minus 1, and 2e to the 2t minus 10. The velocity vector has the components 4e to the 2t, 2e to the 2t, and 4e to the 2t. The speed is given by the magnitude of the velocity. S for the speed is equal to the square root of 16e to the 4t plus 4e to the 4t plus 16e to the 4t, which reduces to 6e to the 2t. My acceleration is another vector. It is the first derivative of the velocity vector, or the second derivative of the position vector. I can take the derivative with respect to t of the velocity components 4e to the 2t, 2e to the 2t, and 4e to the 2t. The acceleration vector is given by the components 8e to the 2t, 4e to the 2t, and 8e to the 2t. Occasionally, I may want to compare the trajectories of two or more objects moving in space. Keep in mind that trajectories are modeled using vector-valued functions, and that these vector-valued functions have a parameter, t, that causes everything to change. This means that the way my trajectory maps out is as important as the actual shape of each curve. In other words, if I have a vector r of t is specified by the components 4 plus t squared, 3 minus t to the fourth, and 1 plus 3t to the sixth on a closed interval a to b, where a is 0 and b is 6, and then I have another vector, capital R of t is given by the components 4 plus the natural log of t, 3 minus 2 times the natural log squared of t, and 1 plus 3 times the natural log cubed of t, on a closed interval from c to d. In order for these two specific trajectories to coincide, the interval cd and the interval ab will not be the same. I can see that by plugging 0 in for t in the little r of t vector, and I get the components 4, 3, 1. But if I try and plug 0 into capital RT, my vector won't be defined at that value. But I can figure out what c and d need to be. I plug in the 0 component in my little r of t vector and I plug in c in my capital R of t vector and compare the first component, I get 4 plus 0 squared is equal to 4 plus the natural log of c. If I solve this for c, I get that 0 squared is equal to the natural log of c, and I must exponentiate both sides to isolate c. I get e to the 0 squared is equal to c, which is equal to 1. So in order for the two components to be equal, in the second vector, my c has to be 1. Likewise, if I plug in 6 in my little r of t vector and d in my capital R of t vector, I get 4 plus 6 squared is equal to 4 plus the natural log of d. Again, I solve for d by exponentiating both sides, and I find that e to the 6 squared is equal to d, so that d is equal to e to the 36. So that for these two trajectories to be equal, the closed interval c to d has to be the closed interval from 1 to e to the 36. Find the closed interval CD for which the trajectory of capital R of t is the same as the trajectory for little r of t over the interval 0 to the natural log of 10. Then find the velocity of both objects and graph the speed of both objects over their respective intervals. The first vector, little r of t, is given by the components 2 minus e to the t and 4 minus e to the negative t on the interval from 0 to the natural log of 10. Capital R of t is equal to the components 2 minus t and 4 minus 1 over t on the interval from c to d. Little r of 0 has the components 1, 3, so that plugging 0 into little r and c in to capital R, I get 1 is equal to 2 minus c, so that c is equal to 1. Then if I plug the natural log of 10 in to the little r vector and d into the big R vector, I get 2 minus e to the natural log of 10 is equal to 2 minus d. This means that d is equal to 10. So in this case, my closed interval for capital R of t to equal the same trajectory as little r of t on the interval from 0 to the natural log of 10 requires that my closed interval CD has to be the closed interval from 1 to 10. My velocity is given by little r prime of t, which is equal to negative e to the t and e to the negative t. The speed is the magnitude of this, and that's given by the square root of e to the 2t plus e to the minus 2t, which is also written as the square root of 2 times the hyperbolic cosine of 2t. The velocity for the capital R of t vector is given by the capital R prime of little t, which is equal to negative 1 and negative 1 over t squared. The speed of capital R of t is given by the square root of 1 plus 1 over t to the 4th. Now I'm going to graph the speed of both vectors. The speed of little r of t graphs like the right half of a shallow upward opening parabola that begins at the vertical axis. The speed of capital R of t graphs as a function entirely in the first quadrant, decreasing from 0 to about 2.5, and then it behaves like a horizontal line at the vertical value of 1 as t increases without bound. While the trajectories coincide for little r of t and capital R of t over their respective intervals, their speeds are quite different. Now you get to try it. Pause the video and find the velocity, speed, and acceleration of the given position vector. When you're ready, restart the video to check your understanding. Your position vector is given by little r of t is equal to the components 3 sine t, 5 cosine t, and 4 sine t for the closed interval from 0 to 2 pi. I want to find the velocity, speed, and acceleration given the position vector r of t is equal to 3 sine t, 5 cosine t, and 4 sine t over the closed interval from 0 to 2 pi. I take the derivative of each component in my vector. R prime of t is equal to 3 cosine t minus 5 sine t and 4 cosine t. The magnitude of this velocity is the speed of my object. This is given by the magnitude of the components 3 cosine t, negative 5 sine t, and 4 cosine t, which is equal to the square root of 9 cosine squared t plus 25 sine squared t plus 16 cosine squared t. This gives me a speed of 5. My acceleration is the second derivative of the position vector, r double prime of t, which is equal to the components negative 3 sine t, negative 5 cosine t, and negative 4 sine t. So this is how we can work with motion in 3 directions using the vector valued functions for position, velocity, and acceleration. Be sure and let me know if you have any questions.